In this video, we're going to cover an entire undergrad physics class in about 80 minutes.
This is an atom. In the center are protons with positive charge and neutrons with neutral charge. And on the outside are electrons with negative charge. Like charges repel each other, and opposite charges attract. And we want to measure how much they attract or repel each other. But there's a problem with that.
In reality, you don't just have a charge floating around like somewhere in space, right? Everything has atoms. So instead what you get is a situation like this, where one object has more positive charges than the other one, so it's kind of a positive region of space. And then on this side, you have more negatives and positives, so you have a negative region. And so now I have a positive region and a negative region, so those are going to want to attract each other. So what you can do is you can take two objects like glass and cloth, and if you rub them together, then the electrons are going to get removed from the glass onto the cloth. So it has more protons than electrons, which means it has a positive net charge. So if I take two charged objects, I can measure the force between them. And if you do that, this is what you get.
The force between two charged objects is proportional to the charge on each of those objects. So if I double the charge on one of the objects, the force between them doubles. If I double the charge on the other one, the force also doubles. If I triple it, the force triples. So Q1 here is the charge on object 1, and Q2 is the charge on object 2. It's also inversely proportional to the radius squared. So if I double the distance between the objects, the force gets cut by a factor of 4. If I make them 10 times further apart, the force is going to go down 100 times. And so now if I combine all of these, what I get is that the force is equal to some constant times each of the charges divided by the radius squared. And this is known as Coulomb's law. And one thing you might notice is that this looks very similar to gravity. In fact, if you look at the gravity equation, you're going to see that it's almost identical, except instead of charges, we're looking at the mass of each of the objects, so M1 and M2. And then also, the constant out front for gravity is a lot smaller. In fact, the electric force is about 100 quintillion times stronger than the gravitational force.
So that's how things would work if you had two charges attracting or repelling each other. What if you only have one charge?
So let's imagine we have a positive charge, and we pick some point out in space and we say, hey, if I were to put a charge here, what would happen to it? Well, we already know the magnitude of the force. It's kq1 q2 over r squared. And we know that they're either going to attract or they're going to repel, which means that the force is going to point from one to the other. So if we make a unit vector, that's a vector with length 1, pointing from the positive charge to our point, we'll call that r hat, we know that this is going to give us the direction that the force is going to go in. And if the charges are opposite, we'll end up getting a negative sign, so the force will point in the opposite direction. Which makes sense, right? Because negatives and positives should attract each other. If we set the charge at this point equal to positive 1, then one of our charges will end up dropping out of the equation. And what's left is the electric field. So the electric field basically tells us how much force we're going to get if we put a positive 1 charge at any of these points. So at this point, the electric field might look something like this, or we could draw the electric field everywhere. And so this is going to show us, hey, if I put a positive charge, it's going to flow away from the one in the center because the positive charges want to repel each other. And you can do the same thing for a negative charge, except now the arrows are going to point inward because our hypothetical +1 charge is going to want to attract the negative. Or you could put a negative and a positive together. And in that case, at every single point, you just calculate the electric field from the negative charge plus the electric field from the positive charge.
If you want to calculate the electric field from a continuous object, all you have to do is break it up into a bunch of tiny charges and then just add up the electric field for each of those charges.
So, for example, if I have a continuous line of charges, then I can break it up into a bunch of tiny pieces and calculate the electric field from each piece. The way you do that is just by doing kq over r squared like normal, except now our q is infinitely small. So we're going to use dq, a differential charge, instead. But what exactly is dq equal to? Well, if we know the total charge on the line, let's call it Q, and the length of that line, then we can get the charge density is just the charge divided by the length. Now, if you multiply that by the lengths cancel and you just get charge. So we can say that the differential charge is equal to the charge density times a very tiny length, dx. And now if we add up the tiny charges with an integral, we can calculate the electric field at some point. And if you want to do it for some other object, you just gotta find another way to break it into tiny charges like this. So if we want to solve this integral, we could pick a point that we want to solve for, call it P, then we can find the radius with the Pythagorean theorem, we can find the r hat vector, we can solve for all of this. And the only problem we're going to run into is that sometimes it's pretty hard to calculate this. I mean, would you want to solve for that? Luckily, there's a much easier way we can solve for the electric field, but to do that, we have to talk about flux. Let's say I have a vector field that represents the wind, and I want to catch the wind with a net. How can I create a way to measure how much wind is caught by the net? Well, we know that if the wind is blowing stronger, then it'll probably catch more. And also, if the net is bigger, it'll catch more too. And then lastly, if the net points perpendicular to the wind, we'll get more. So in order to describe this, we'll need to get the net's area vector, which is just a vector that's perpendicular to the net's area, so the circle right here, and then the length is equal to the area. So if the circle here, has an area of 5, then the vector is just going to have a length of 5. If either the wind is bigger, the net's area is bigger, or if they point more in the same direction, then we'll catch more wind, which means that we can write our ability to catch wind as the dot product of the wind and the area vectors. And this is exactly what flux is. It's just how much a vector field flows through a given area. And if you have a more complicated surface, then you just need to break it up into tiny areas, dAs, and then add up the flux across the whole surface. So you get integral of W dot dA. Now the electric flux is just how much electric field flows through an area. So to calculate electric flux, we'll start with the charge and we'll surround it with a sphere like this. And to make things easier to see, we're going to draw it in 2 dimensions, but remember that we're really making a case for 3 dimensions. We've already seen that the electric field for a positive charge points outward because it repels that hypothetical +1 charge. And our goal is to find the electric flux on this sphere. So to do that, we're first going to restrict our view to the electric field on the surface of the sphere, so like this yellow region right here, and we can see the differential area vectors are going to point out away from the sphere because they have to be perpendicular to that surface. Writing out the flux equation, we get this, where the circle just means that we're adding up over a closed surface. Since both the electric field and the area vectors always point away from the charge in the same direction, then we can simplify this from the dot product to simply the scalar product, EDA. Now recall that the electric field is a function of radius, but in the case of a sphere, the radius is constant, which means that we can pull the E out of the integral like this. And now we're left with just the integral of differential area, which means that this can simplify to area, and the entire flux through the sphere ends up becoming EA. So now we can start plugging things in. For the electric field, we have kq over r squared. For the area of our sphere, it's 4 pi r squared. We can cancel out the r squareds here, and then we'll also usually rewrite these constants, 4 pi and k, as a new constant, 1 over epsilon naught. And this is Gauss's law. The electric flux is equal to the charge inside the sphere divided by epsilon naught. And the thing that makes this powerful is that it also works for any closed surface, usually called a Gaussian surface, not just a sphere. To see why, we can surround the sphere with a completely general surface. As long as it's closed, it doesn't matter what kind of surface it is. Now, we'll extend 2 line segments from the charge to each of the surfaces. We'll call the area enclosed by the sphere A1 and the area enclosed by the general surface A2. The radius to the sphere is called r, and the radius to the general surface is called some scaling factor n times r. Now, as we've seen before, we can rewrite the dot product in its cosine form. So the electric flux for the second area is equal to the electric field at the second area times the cosine of theta times some small area 2, all added up across the second surface. Now the angle theta is this one right here, and it points between the electric field and the area vector A2. Now the component of A2 that's perpendicular to the electric field looks like this blue circle, and in fact it's the same as A2 times the cosine of theta. To see why, let's look if theta is 0. In this case, the cosine will end up going away because it's 1, and we'll just get the electric field times the area, so it's the same as the perpendicular component. Now if the angle is a right angle, then the cosine will be 0, and there will also be 0 perpendicular component. So we can rewrite the flux integral as the accumulation of the electric field at surface 2, E2, times some differential perpendicular area. Now remember that the electric field goes like kq over r squared. So if our radius is now n times r, we'll introduce a factor of 1 over n squared into the equation. Now another thing we can do is we can pull out the projection of these two line segments into areas. And then we'll get two triangles that overlap each other like this. We'll call the length of the middle segment d, the diameter of area 1, and since the triangles overlap like this, they're similar triangles, which means that the ratios of the side lengths have to be the same, and so the length of the top segment has to be n times d. And this is the diameter of the perpendicular area. So now, if you recall that the area of a circle is pi r squared, which is the same as pi times half the diameter squared, if the diameter increases by a factor of n, then the area has to increase by a factor of n squared, which means that our dA perpendicular is the same as dA through the first sphere times n squared. Now we can cancel out the n squareds in the integral, and we have the exact same flux integral as the sphere, which means that the electric flux through A2 must be equal to the electric flux through A1. And this will hold true for every single dA as we integrate across our general surface. Now let's take a minute to think about what would happen if we had another charge inside the surface. So we could surround it with a sphere, just like we did before, and we can make the exact same flux argument. And since the fluxes are going to add because the electric field adds, then we would find that the flux is now just the sum of the flux from the charge. So we could say that the flux must equal the total charge enclosed by the surface divided by epsilon naught. And just for completeness, if we have a charge that's outside the surface, say over here, then it'll have a flux that goes both into and out of the surface. So if we use the same arguments, the amount of flux going into the surface has to equal the amount of flux going out of the surface, and so they're going to cancel with each other, leaving us with zero net flux for charges that are outside the surface. And so now we have Gauss's law. The electric flux through some closed surface around some charges is equal to the charge enclosed by the surface divided by some constant. And now we can calculate the electric field much more easily. So let's look at an example. Let's say I have some large sheet of charge. Now the electric field on the sheet of charge is going to point away from both the top and the bottom, like this. So if we want to find the electric field some distance away from the sheet, we'll need to create a Gaussian surface. So we're going to go ahead and bring in the cylinder. And then just to simplify things, we're going to go ahead and make each of these one vector, and we'll make them go through the cylinder like this. As a reminder, here's Gauss's law. Now we're going to go ahead and start solving the left side. Since we're at a constant distance from the charge along the cylinder, and the electric field is always perpendicular to the surface of the cylinder, then this integral simplifies to E times A, where A is the area of both the top and the bottom circle. So we get 2 pi r squared with the E out front. Now for the right hand side, we'll have to make some assumptions. Specifically, we'll go ahead and say that the whole sheet has a charge Q, and the whole sheet has an area A. The charge density, sigma, is the charge per unit area, so Q over A. And if we want to get the charge, we just have to multiply by the area. So the charge of the region enclosed is sigma times pi r squared, since pi r squared is the area of the circle that encloses the charge. And don't forget to divide by epsilon naught. Now we can set these two equal to each other, cancel out the pi r squared, and divide by 2. We'll get that the electric field is equal to sigma over 2 epsilon naught. And that's it. It's a much simpler calculation.
And now we have to talk about voltage, which is kind of like potential energy, but for charges.
If I have some object, like a square, and I apply a force to it, and it also moves some distance from that force, then I can find the work as the force times the distance times the cosine of the angle between them. So, if the force and the distance are in the same direction, the work is just the force times distance. If the force is perpendicular to the displacement, then there's no work. And if the force is in the opposite direction of the displacement, then there's negative force times distance work. So the work really measures how much the force and the displacement are aligned with each other.
So if you think about the potential energy of this ball, right now I'm holding it up, which means it has the potential to fall down, right? And if I pull it higher up, it's going to have more potential energy because it can fall further down. So mathematically, what we kind of say is you have the force of gravity pointing downward. So when I move it against the force of gravity, so the displacement is upward, but the force is downward, I've created potential energy because now it has the ability to go backwards following the flow of gravity.
So this means that when you do negative work, you get potential energy. And we're also going to go ahead and rewrite the right side as a dot product just because it's a little bit more compact. Now if the force changes as we move along the path, then you can add up the work done by each little point in the path. So you can add up the work from delta S1, delta S2, delta S3, and you can imagine that if we add up all of these and then we make the distances as small as possible, then we're going to get the best approximation that we can. So the potential energy ends up being this integral. And if we want to solve for the electric potential energy, we can go ahead and put in the electric force equation we have, and then our change in distance, we're just going to make it go in the r hat, the radius direction. So if we bring it in some small change in radius, dr, in the r hat direction, we'll start with the two charges infinitely far away from each other, because if they're infinitely far away, they're not going to really exert any forces, so they're not really going to have any potential energy. And we'll bring them in to some radius r prime. So if we go ahead and we solve this equation, what we get is that the potential energy between two charges is going to be k, q1, q2, over the radius between them. Now we're ready to talk about voltage, because voltage is just the potential energy per unit charge at some location. So just like the electric field was asking, hey, what force would I get if I put a +1 charge here? The voltage is saying, hey, what if I put a +1 charge here? What's the potential energy going to be like in that situation? Now if you look at the equation on the top, you can see that we can also solve for voltage by dividing both sides by the charge. On the left-hand side, we'll get potential energy divided by charge, which is just our voltage. And on the right-hand side, we'll get a 1 over q. But if you notice, there's also the force here. If we have the force per unit charge, what we end up getting is the electric field. So now if we simplify this equation, we can see that the voltage is just the negative of the accumulation of the electric field across some distance. So that means that if we take some charge in the electric field and we move it against the electric field, we create voltage or electric potential, because now the charge has the ability to flow along the field back in the direction it came from. If we want the absolute voltage, we'll have to do the same thing where we go from infinity to our radius r prime. But if we just want the change in voltage between two locations, then we could just go from location A to location B. And there's another thing to notice here. So remember how earlier we said that if they're perpendicular, then there's going to be no work. Well, this also means that if the electric field and our change in distance are perpendicular, then there's going to be no change in voltage. So if we go back to our original electric field here, and we draw lines perpendicular to the electric field, all of those lines are going to be at the same voltage, which is why we call them equipotential lines, same voltage. So we can go ahead and label these. Maybe the left side is -1 volt and the right side is +1 volt. You know what this looks a lot like? A contour plot. Except instead of elevation, we have voltage. But what if our voltage was our elevation? Well, then we would have something like this, kind of like 3D map of the voltage, where you can see that positive charges kind of push up and create hills, and the negative charges stretch downward and create valleys. And since the electric field points perpendicular to the contours, because the contours are perpendicular to the electric field, right? They're kind of perpendicular to each other. Then the positive charge is always going to be following the path of steepest descent. So what we can imagine is if we bring in a positive charge up at the top of the hill here, then it's going to follow the path of rolling downward into the valley, because that's where the voltage is the lowest, so it's decreasing its potential energy. Now if we had a negative charge, and we put it at the bottom of this valley here, it's actually going to roll upwards, because you think all of the signs are flipped and we have a negative charge. So another thing you can notice here is that these charges aren't actually going to care how high or how low the hill is, right? When they're rolling down the hill, the only thing that matters is that lower down on the hill is lower than where they are.
And so if you have a 9-volt battery, what it really means is that one end has 9 volts of more potential energy than the other end. Not that it's at exactly 9 volts, because you can kind of pick wherever you want to be 9 volts. But that also means that if you get 2 and you connect them together, then this side is 9 volts higher than this end. But also, This end, the end of this bottom battery, is 9 volts higher than this end, which means that across these two, you have 18 volts. Now, if you get a piece of pencil lead and you connect it across them, what you should notice is that it starts catching on fire a little bit. You see that? And the reason is because it has a low resistance.
But before we talk about that, let's take a minute to review what we've learned so far. So we've seen four main quantities. The first is force, which is a push or pull on an object. And between two charges, it's some constant times each charge divided by the distance between them squared. Electric field is the force that would occur at some location if you were to put a +1 charge there. One of the charges ends up dropping out of the equation, so we get some constant times q over the distance squared. Voltage is the electric parallel to potential energy. Specifically, it's the potential energy if you were to put a +1 charge at some location. And potential energy is the ability of some object to do work. So when you push something against a force field, you create potential energy because now it can move through the force field. We can get between electric field and force by adding or removing a charge. So we end up multiplying or dividing by Q. We can get between voltage and potential energy by adding or removing a charge. So again, multiplying or dividing by Q. You can go between electric field and voltage by adding up the negative accumulation of the electric field or finding the slope of the voltage. And then we get between force and potential energy by, again, adding up the accumulation or taking the slope. Take a minute to make sure you're comfortable with this, especially the bottom two quantities, since those are going to basically show up for the rest of the video. So if I have a battery here, and I connect the two ends, then we would expect the electrons to move from one end to the other, because that would decrease its potential energy. Now we also know that the electrons don't just jump to the other end all at once, because, well, batteries don't just burn out the second you connect them. Which means that there must be something stopping the electrons from instantly jumping from one end to the other. And that thing is resistance. So resistance really measures the proportionality between the voltage applied and the flow of electrons. But what exactly is the flow of electrons? Well, one way we can measure them is the amount of charge that passes through some area in a certain amount of time. So the change in charge over the change in time. Now we can also define it geometrically. So the charge inside here is equal to the charge per volume times the volume. Seems simple enough. Now we'll rewrite the charge per volume as the charge carrier density, so something like 10 atoms per cubic centimeter, times the charge on each carrier. So maybe the charge on an electron would be the charge on each carrier, and then again multiply it by the volume. And then we're going to also go ahead and rewrite the volume as the area times the length, where the length is the same thing as the velocity times some change in time. Now why did we go through all this rewriting? Well, it's because now we could just divide both sides by the change in time. And now we'll get that the flow, which is the change in charge over change in time, equals the number of charge carriers, N, times the charge on each of those carriers, Q, times the cross-sectional area of the wire, A, times the velocity of each charge carrier, V. And by the way, this flow is also called current. Another thing we can do is solve for the velocity of the charges in the wire. So let's do that. So we can divide both sides by N, Q, and A to solve for the velocity. And now we'll pick some sensible values and solve for each of these. If you do all the calculations, you get 0.2 millimeters per second.
But how does that make any sense? I mean, if I turn on a light switch, it's almost instant.
Well, that's because you don't have to send a charge through the whole circuit in order to get it going. Instead, it's like a big old conga line, where one charge goes in and one charge goes out. And that process happens almost instantly, which means that the circuit can start and stop almost instantly. And with a good idea of current, we can get back to resistance, because resistance is just how much voltage is required to get a certain amount of current out. So for example, if my resistance is 2, then I need 2 volts to create 1 amp of current. And the equation that we found is usually written like this, and it's called Ohm's law. Voltage is equal to current times resistance. If we can find any 2 of these quantities, then we can solve for the other.
So in practice, if you're going to go build a circuit, you'll get some resistors that look like this. So these are around 200 ohms. This is what a single one looks like. And then you insert them at different parts of the circuit to control the resistance.
So if I'm trying to build a circuit, I can start with a voltage source. This is the symbol for voltage, by the way. And then I'll connect it to resistor R1 and also resistor R2. So if R1 and R2 are different, then what's the current going to look like? So to do that, we can take a look at the geometric definition of a resistor. So remember that in practice, a resistor makes it hard for the electrons to flow through by creating thermal energy. So basically, it's like a constriction in a pipe. So if it's longer, then the electrons are going to have more resistor to go through before they reach the other end, which means that there's going to be more resistance. But if it's wider, then there'll be more paths for the electrons to go through, so they'll flow through more easily. So what we can say is that resistance is proportional to the length of the resistor and inversely proportional to the area of the resistor, or that the resistance is equal to some constant times length divided by area.
And if you ever need to get the resistance of some weird object, then you're just going to add it up across each differential length as we've seen before.
So when we put two resistors in series, one after the other, then we're effectively creating a larger resistor with a larger length. Since the resistance is proportional to length, we can get the effective resistance by just adding R1 and R2. So if our voltage is 9, R1 is 1, and R2 is 2, then the effective resistance is 3, and the current is 3 amps. Another way we can combine the resistors is like this, called in parallel. Now we're effectively increasing the area of the total resistor. Since the resistance is inversely proportional to the area, we add up the inverse of R1 and the inverse of R2, which gives us 1 over R effective. And now we invert both sides, we get the effective resistance. With these two methods, you can pretty quickly break down the resistance of a complicated circuit. So like this one right here. R4 and R5 are in series, one after the other, so we can add them up. R4, 5 and R6 are in parallel, so we can add their inverses. R2 and R3 are also in parallel, so we can add their inverses.
And lastly, we can add up the 3 remaining resistances since they're in series. Another useful metric in circuits is the power, or change in energy over change in time. So if the energy changes by 5 and 5 units of time, then my power is 1. So we can get power by multiplying current, which is change in charge over change in time, by voltage, which is energy per unit charge. And if you combine it with Ohm's law for an ohmic resistor, you can see that there are 2 other ways to write this. And now we can see why the battery caught on fire, because if the voltage is constant, then the power is inversely proportional to the resistance. So something that doesn't resist current flow that much will get a big spike in energy, and as a result it'll start smoking up. But not all of that current flow is equally distributed. If you have a parallel circuit like this, some of the current will go to the top path, and some will go to the bottom path. And they won't exactly be the same, because more current is going to flow through the lower resistance path. Since charge is conserved, we know that the total current going into both paths must be the same as the total current flowing out of both paths. And since energy is conserved, the change in voltage as you take either path should be the same. Using these 2 equations will usually work for you, but sometimes it's not enough, like in this circuit. And in that case, you're going to want to use the Kirchhoff equations. Wait.
Kirchhoff.
Oh no, there ain't no way I'm going to be able to pronounce that. So the first Kirchhoff equation says that at a junction, which is where the wires meet, the total charge going in must equal the total charge going out. In other words, current in equals current out because the charge has to go somewhere. The second one tells you that if you start and end in the same place, then you should have the same potential energy. So if you go through a big loop in the circuit, then the voltage gain from the battery minus the voltage drop from each of the resistors, which is equal to I times R, must equal 0.
Now so far, we've been assuming a perfect battery, which means that we get a constant supply of voltage no matter what happens. But in reality, sometimes the voltage can fluctuate a little bit, which means it's useful to have a system that can continue to power the circuit during those fluctuations. A capacitor.
Now a capacitor is just a component that's 2 connected metal sheets. And if you put it across a voltage source, then the charges are going to flow to the sheets since they're attracted to the other side. But when they reach the sheets, the same sign charges on the opposite side are repelled, so they basically continue across the circuit, although it's not exactly the same charge. However, now there's more positive charge on one sheet and negative on the other sheet, which means that over time, the capacitor will eventually reach equilibrium when it has a voltage across the plates that's directly opposing the voltage created by the battery. The The quantity we use to measure capacitors is the capacitance, C, which is equal to how much charge, Q, you get on the plates when you apply some voltage, V. Now if you want to know exactly how much charge is going to be on the capacitor over time, then we could break it down with a Kirchhoff loop. So remember that means the voltage over a full loop is 0. So the voltage from the battery, V, minus the voltage drop from the capacitor, which we can get from C equals Q over V, voltage is Q over C, and lastly we subtract the voltage drop from the resistor, I times R. Also remember that the current is just the change in charge over change in time. So if you rewrite it like this, we have a differential equation. If we go ahead and solve it, we get this exponential decay or kind of carrying capacity function, which looks like this. So in the beginning, the charge accumulates very quickly, and then it levels off over time as the capacitor is fully charged. And you can also look at the current, which is the slope of the charge curve. In the beginning, a lot of charge is flowing through, and over time it goes to 0 because the capacitor is opposing the voltage from the battery. In a setup where we want the circuit to account for voltage fluctuations, we put them in parallel like this. So when the battery is turned on, at first the current's going to go through the capacitor, charging it up, and then eventually it'll divert to the rest of the circuit. If the voltage source goes out, then the current will continue to flow from the plate to the capacitor. We can go through the same procedure with a Kirchhoff loop equation, and we get the expected result of exponential decay. So it starts off with lots of charge and then quickly gets rid of it through the resistor. That also means that the current is quickly flowing through the capacitor, or really out of the capacitor, into the circuit, and then it levels off over time. Now we could also use the other ideas we've discussed to find the current through the resistor. But in general, you can usually get away with thinking the capacitor is acting like a wire in the beginning when it's charging up its plates, and then over time, it's going to eventually turn into a sort of break in the circuit because it's opposing whatever voltage was applied across it.
But what happens if you put two capacitors together?
So once again, we can look at the geometric definition of a capacitor. We'll call the area of each plate A and the distance between the plates D. Now if you recall from the Gauss's law example from earlier, the electric field of a single plate is the charge density, sigma, over 2 times epsilon naught. So for 2 plates, you're just going to get sigma over epsilon naught. And the charge density is the same thing as charge per area. So we can rewrite this as Q over epsilon naught A.
And remember that epsilon naught is just a constant.
To get the voltage, we can add up the accumulation of the electric field along some length. This simplifies to just E times the length since the electric field is constant. So in our case, the voltage is Q D over epsilon naught times A. And now remember that the capacitance is just charge divided by voltage. So if we plug in our voltage expression, we'll get that the capacitance is equal to epsilon naught A over D. In other words, it's proportional to the area and inversely proportional to the plate-to-plate distance. So if we have 2 capacitors in parallel, then we effectively have one big capacitor. Since capacitance is proportional to area, the effective capacitance is just the sum of each capacitance on the parallel capacitors. Now if they're in series, we're effectively increasing the plate-to-plate distance. Since distance is proportional to 1 over c, we add the inverses of the capacitances and invert the whole result to get the effective capacitance. So in practice, it's the opposite of resistors. If they're in series, you add their inverses, and if they're in parallel, you just add them up.
Now sometimes it's useful to get the energy of a capacitor, and to do that, we can just add up voltage times charge, because those cancel out and we get potential energy. So using the C equals Q over V equation, and plugging in our capacitance, we can get several ways to write the energy. Now if you want to, you can also rewrite the equation 1/2 CV squared like this, and divide both sides by A times D, which is the same thing as the volume. This will get you the energy per volume, or the energy density of the electric field in the capacitor.
Now, a real capacitor doesn't have parallel plates. Instead, they're coiled up into a little cylinder like this. And in between the plates, they don't just have air. Instead, there's an insulating material, which is one that doesn't conduct electricity.
To see why, let's take a look at what happens to the insulator when you insert it. While it can't conduct charges, the atoms can reorient themselves, which means they'll take this configuration since the opposites attract. On the inside of the material, the pluses and the minuses cancel, but on the outside, you get a small electric field pointing like this, opposite the electric field from the capacitor.
Since the voltage is derived from the electric field, a weaker electric field means less voltage. So now we have the same amount of charge on each plate for less voltage, which means our capacitor is more effective. So basically the insulator, also called the dielectric, weakens the electric field by some factor kappa. And one way you can think of this is that it changes the permittivity constant from epsilon naught to kappa times epsilon naught.
So I got a circuit right here. It's got some capacitors, resistor, there's a light bulb right here. And the outlet is actually just a voltage source. So if I go ahead and I plug this in.
Okay, so it turns out that the voltage in your wall uses alternating current. So instead of the voltage looking like this, it looks like this. So for some general AC circuit, it's going to look like a normal sine wave, scaled up by a factor V0, sped up by the angular frequency, omega, and shifted by a constant delta. And in our case, we're just going to ignore the delta because it's going to make the math a little bit easier. V equals IR still applies here. So if you've got a resistor, then you can find the current pretty easily. It's going to line up with the voltage. Wall outlets are usually like 100 to 300 volts, but they kind of vary around the world. And you can already see there's a problem here. How do I go from this wiggly sine graph to a constant number like 100? We can't just take the average of the graph because all sine waves have an average of 0. So instead, what we have to do is square the wave, then take the average, then take the square root of that average. And this is called the root mean square, or RMS, and it's usually the quantity people are referring to in AC circuits. So when you see that the wall voltage is around 100 to 300 volts, that means that the root mean square voltage is 100 to 300 volts. Ohm's law and the power equation are going to work just fine if you use the root mean square quantities of everything. But what if I have a capacitor? Well, in a low frequency situation, the capacitor is going to get to charge up, so it's going to oppose the current flow a lot of the time. But in a high frequency situation, it's not going to have enough time to fully charge up, so it's going to let more current through as the AC circuit's running. So the opposition to the AC current is inversely proportional to the frequency. And also, the better capacitor you have, the more it's going to charge up, right? Because it can get more charge per voltage as the voltage increases and decreases. So the better a capacitor you have, the more it's going to be charging up and discharging over time, which means that it's not going to be opposing the voltage as much in an AC circuit. You can work this out from the definition of capacitance in the sine wave, or you could just look at the proportionalities and kind of think about it. But in both cases, you get that the proportionality between current and voltage is this quantity 1 over omega c. It's like resistance, but it depends on how quickly the circuit's changing, and we call it reactance. And the symbol we use for reactance is X. So if you have a smaller capacitor or a more slowly changing circuit, then there won't be as much max current when you apply some max voltage. And because of these relations, the current on a capacitor is always going to lead the voltage source by 90 degrees, if you look at the sine waves. To see why, let's walk through what's happening here. When we first turn on the voltage, the capacitor acts like a wire, so it very quickly starts running current and accumulating charge. Then, the voltage starts to level off, and the current starts to level off too. The maximum charge stored on the capacitor occurs right here when you have maximum voltage, and you can see this since the charge is the area under the current curve. So right before the current goes negative, it's going to have the maximum charge. Now when you start decreasing the voltage, the capacitor has excess charge on it, so to get rid of it, it's going to start discharging by sending current in the opposite direction, which is where we get the negative current from. And it'll keep discharging more and more until the voltage reaches 0. At this point, the areas under the curves cancel, which means that there's no charge on the capacitor right now. So when the voltage starts going negative, it's going to act like a wire again, quickly drawing lots of current, except now it's in the opposite direction. And now we have the same cycle repeating, but for negative charge and negative current. A different way to imagine this is to show the sine waves as spinning vectors like this, where the vertical axis represents the voltage across the circuit. So the voltage might look like this.
Our maximum voltage is V0, since that's the value when the wave hits the top. And omega t is the angle under the vector right here, and represents how far along the wave we are. So it starts at 0, and then increases as we go along the path.
And the height is the voltage, V0 sine of omega t, because the sine is the opposite over hypotenuse. The opposite is the voltage here, and the hypotenuse is the maximum voltage V0. Now the capacitor, as we said before, will be 90 degrees ahead, so we could show it vertically like this. Now if you have a capacitor and a resistor in the same circuit, we know that the resistor will follow the voltage, and we also know that resistors in series add. So we can get the total resistance, in this case called the impedance, since it also relies on the frequency, by adding the resistance and the reactance vectors. The magnitude of the impedance is equal to the length of the vectors added together, and since they're always perpendicular, it's the same as the length of the hypotenuse of this right triangle. Z equals square root of x squared plus r squared, where z is the symbol we use for impedance. So basically, impedance measures how much current you get when you apply a certain amount of voltage, but in AC circuits, the frequency also matters, which is why it's a different quantity than resistance. And now that you know about AC circuits, you can connect stuff into a wall and you'll be okay. Probably. Maybe. Some types of metals can be magnetized, which means they have a north pole and a south pole. Opposites attract, and similar poles repel. And just like the electric field, we can have a magnetic field, which tells us what would happen if we put a north pole there. Now here's the thing, moving charges also create magnetic fields. That's how the Earth's magnetic field works. And you can figure out how strong the magnetic field is going to be and what direction it's going to point in with the Biot-Savart Law. So let's break it down. dB is a small slice of the magnetic field. The fraction out front is just a constant, so we're going to go ahead and ignore it for now. The cross symbol represents a cross product between dl and r, and its magnitude is the magnitude of each of the vectors times the sine of the angle between them. But the direction can be found with the right hand rule. Take your right hand, point it forward, point your thumb up, and point your middle finger to the left. Now you have a right hand rule. If A cross B equals C, then your pointer finger is in the direction of A, your middle finger is in the direction of B, and your thumb is the output, the direction of C. Back to the Biot-Savart Law, this means if you point your index finger in the direction of the wire, specifically the direction that positive charges go, and your middle finger in the direction from the wire to the observation point, then your thumb points in the direction of the magnetic field. And at this point, I feel like it's worth mentioning that conventionally, current goes in the direction of positive charges. So anytime you see something about current and its direction, you always assume that it's going to be the positive charges that are moving, or in the opposite direction of the electrons. And anytime you see dl along a wire, it's going to be following the current. Lastly, the magnetic field is proportional to the current. So, more current, more magnetic field, and inversely proportional to r squared. So the further out you get, the weaker the magnetic field. Because of this law, the magnetic field is always going to curl around the wire of current like this. So another right hand rule you can do is make a thumbs up like this. Point your thumb in the direction of the current, and your other fingers will curl in the direction of the magnetic field. Or, if you want to, you can point your thumb in the direction of the magnetic field, and your fingers will tell you the direction of the current. This means that if you want to create a fairly consistent magnetic field, you can make a loop of current, like this. Putting it all together, to get the magnetic field of some running current, you add up the current times a small bit of length crossed with the radius, divided by the radius squared. In other words, moving charges create curling magnetic fields. Now here's the weird thing. Magnetic fields also move charges. Specifically, the force on a charge from a magnetic field is equal to Q V cross B. This means that if a particle isn't moving, or has no velocity, then there's no magnetic force. Or, if the particle is moving parallel to the magnetic field, there's also no force. But once the particle starts moving slightly perpendicular to the magnetic field, then the charge experiences a force that's perpendicular to both its velocity and the magnetic field, specifically with the cross product. Now in this segment, we're going to be working a lot with three-dimensional vectors, which we usually represent as arrows. At the front of the arrow is a pointed tip, and at the back of the arrow is what's called feathering. So when an arrow points out of the screen, we draw a circle and a dot like this. And when an arrow points into the screen, we'll use a circle with an X, which represents the feathering. So here's a question. If I have an electron going out of the screen and a magnetic field pointing to the right, in what direction is the force going to be in? Now's your chance to figure it out. Okay, time's up. Since the force equals QV cross B, we can point our index finger the direction of velocity out of the page and our middle finger to the right, and this means that V cross B points upwards. But remember that electrons have negative charge, so the upward pointing force gets inverted and the electron actually experiences a downward force. Now that we know what forces act on a charge in a magnetic field, the next logical thing to do might be tracing out its path. So, let's assume we have a magnetic field pointing into the screen, and we'll send a positive charge upward to the right of it. Using the force equation and the right-hand rule, we can see that the force is to the left, so the charge will get pushed to the left until its trajectory looks like this. Now, its velocity is to the left, so if we do the right-hand rule again, we get that the force is downward, which pushes the charge downward until it's going down and to the left like this. Now the force is to the right, so it goes like this, and then the force is up. So, we can see that the charge follows a circular path. It's important to note that the magnetic field the charge creates won't push the charge itself, otherwise you'd have some kind of weird feedback loop thing. On each side of the charge, there's an equal and opposite magnetic field, which means that the force is going to cancel in all directions. If you have some general velocity and a straight magnetic field like this, you can break it into the components of the velocity, parallel and perpendicular to the magnetic field. The parallel component won't create any force, so the charge will just keep going in that direction. The perpendicular component will curl the charge in a circular shape, so when you combine them, most charges will follow a helical path when going through a magnetic field. This is how the northern lights work.
Charges in the atmosphere get curled into a helical path because of the Earth's magnetic field, and for reasons we'll see in Chapter 4, these accelerating charges create light waves.
Now of course this is only for a single charge. If you have a wire of charges, then you'll have to take the charge inside the wire. We've seen before that we can rewrite it with this geometric definition.
So the charge inside the wire is equal to the charge carrier density times the charge on each carrier times the volume, or area times length.
And if we let the length vector point in the same direction as the velocity, then we can swap them since the magnitude and direction are both preserved. And now the constants on the outside are just the current,
because we go from length to velocity by dividing by the change in time, which is also how you get from charge to current.
And if the magnetic field changes across the wire, then we can just add up the force across tiny lengths of the wire like this. So we get that the magnetic force acting on a wire of current equals adding up the current times a small bit of length crossed with the magnetic field across the whole wire. So here's a problem. I have a device that can measure the voltage just fine, but I don't have anything that can measure the magnetic field. Well, what I can do is I can position the magnetic field perpendicular to the current like this. Now the positive charges are pushed upwards, and as more positive charges start to accumulate at the top, they create an electric field, which opposes the magnetic field force until they're equal. So once they're equal, we know that the magnetic field force is equal and opposite to the force from the electric field. So Q times E should equal QV cross B. And since the current and the magnetic field are perpendicular, this simplifies to just QVB. Now we can cancel the Q's on both sides, and remember that the voltage is the accumulation of the electric field. We'll assume that the electric field is constant, in which case we get the voltage equal to the electric field times this distance, or that the electric field is the voltage divided by the distance. Substituting this in, we can solve for the magnetic field in terms of the voltage. We can calculate the velocity just like we did earlier, somewhere around 0.2 millimeters per second. Another example is two parallel wires like this. The bottom wire creates a curling magnetic field,
which points out of the screen near the top wire above it.
So our IDL cross B points downwards, which means that the top wire is getting pushed downwards. Likewise,
the top wire creates a magnetic field that points into the screen near the bottom wire.
So IDL cross B points upwards. The bottom wire is pushed upwards. So we can see that parallel currents attract each other. As a third example, let's look at a charged up capacitor, and we'll add some long wires extending from them to the left like this. Now, we'll add a magnetic field pointing out of the screen with something like maybe a permanent magnet in between the two wires. Lastly, we'll connect the circuit with a piece of wire that can move. So really anything that's conductive and metal will work. With a small resistance, we know it'll draw a lot of current. So this large current I times dl cross b will then act as a large force to the left. And what we'll get is that the metal piece gets very quickly accelerated to the left. For one last example, let's put a loop of current inside a magnetic field, like this. We want to compute the torque on the loop, which is the same as the radius crossed with the force. If you push from further away or with more force, then you get more torque, which is going to want to spin the loop. Specifically, we'll want to get the torque that makes the loop spin on its top axis. So the force from the top and bottom wires both act vertically. Since those are parallel to our vertical axis, they're not going to create any torque around that axis. We can now limit our focus to just these two vertical wires. Let's take a look at the top-down view. We'll rewrite the cross product as R times F times the sine of the angle between them. Now, we know that the radius is just half the width of this top wire. So, we can rewrite it as W over 2 F sine theta. And there's two of them since we have two forces from each wire. So, when we combine them, we get WF sine theta. Now, the force we've seen before is IL cross B. And since our magnetic field, which points to the right, and our current length, which points out of or into the screen, are perpendicular, then F just becomes ILB. Now notice that width, or W, times L is the same as the area of our loop, so we can rewrite it like this. Now lastly, we'll define a vector called mu, which has magnitude I times A times N, which represents the number of loops if we were to have a multiple loop coil. The cross product of mu and B is the torque on our loop. This holds for any loop of current, and it's how motors work.
Now earlier, right after we talked about electric field, we did flux, and then we did Gauss's law. And you can do the same thing here, but the result isn't really that interesting.
Magnets always have a north pole and a south pole. If you cut one of them in half, you just get another north and another south pole. So any region of space is going to have a magnetic field flowing away from a north pole and towards a south pole. In other words, there's always going to be flow into and out of some region, and the exact amount makes it so that the flux always cancels. The magnetic flux of any closed surface is zero. A more useful thing for calculating the magnetic field is the magnetic circulation. Instead of looking at how much field flows through a surface, and so how much it flows parallel to the area vector, we look at how much it flows along a given path. Basically, at each point in the path, we assign a length vector, dl, that points in the direction we're going, and then we compare that to the flow of the magnetic field. So for example, if I have a wire of current here, you can imagine it would have a lot of circulation along this circle here. Knowing the circulation allows us to use something called Ampere's law. The circulation on any closed path around a loop is proportional to the current running through that path. To see why it's useful, let's look at an example. If we go in a circle of constant radius around the wire, the magnetic field will be constant. So just like Gauss's law, we can pull out the magnetic field, and now the integral of dl is just the length of the wire, or the circumference, 2 pi r. Divide those sides by 2 pi r, and you get the magnetic field around a wire. Notice that instead of an inverse square law, like we're used to seeing, the magnetic field decreases only inversely with radius. Thinking back to the Biot-Savart Law, this is ultimately because we have a radius vector in the numerator, magnitude-wise, so it'll cancel with the r squared in the denominator, giving us effectively a magnetic field inversely proportional to the radius. So the magnetic field still drops off pretty quickly, as you can see by looking at the graph of the strength. Alright, now it's time to talk about how basically all major electricity sources generate that energy. Are you ready for the secret? Take a piece of wire and wrap it up into a big coil, and then take a magnet and move it around inside the coil. That's it. If you can find some way to move the magnet or the coil, you got electricity. The mechanism behind this is called Faraday's law. The voltage imposed on a loop of wire is equal to the negative of the change in flux over change in time. So if you increase the magnetic field, you get a voltage in the negative direction. If we want to, we can break this equation up into its raw form. We'll write out the magnetic flux completely, as well as the voltage. In this case, it's conventional not to use the negative sign on the voltage so that the directions work out. Notice that the magnetic flux is not going to be zero since we're not going through a closed surface, we're looking at the flux through a loop. Also, if you remember from earlier, we got this voltage equation from the force from the electric field. Q times E, but we have a new force too, QV cross B, so we have to add that into the equation. Now this equation isn't really that easy to work with, so we're usually going to stick with the original one. Anytime I change the magnetic flux in my current loop, I get voltage. So looking at the flux integral, there are three main ways I could do this. I could make the magnetic field weaker or stronger, I can make the area bigger or smaller, or I can make the loop in the magnetic field point more or less parallel. Another thing to take note of is the negative sign. The direction that the voltage takes will oppose the changing flux. So if I have an increasing flux in this direction, then the voltage will point in the direction that would create an opposing magnetic field. This is called Lenz's law. You can also use the right-hand rule to figure out which direction the current's going to point in. First, determine the direction the magnetic flux is changing in. So for example, if you start with a strong magnetic field upwards, but it weakens, then your change vector is downwards. Now, point it in the opposite direction, since the current opposes the change in flux. You point your thumb in that direction, then your fingers curl in the direction of the current. One consequence of this is something called eddy currents. If you have a magnetic field, such as this one pointing into the screen, when you move a metal object into the magnetic field, the field through the metal gets stronger, pointing into the screen. To oppose this, the voltage is created in the direction out of the screen, counterclockwise. Now there's also current in that direction, most of which is pointing upwards as the object enters the magnetic field. Using our original right-hand rule, we have upward current and a magnetic field into the page. This creates a force pointing to the left on our piece of metal, which opposes the motion into the plate. Now when the metal moves out of the plate, the magnetic field gets weaker, so the change vector points out of the screen. To oppose this, voltage points into the screen, or clockwise, which also creates upward current and a leftward force on the left side of the metal, opposing the motion out of the magnetic field.
Alright, so now we're going to talk about Tesla coils. Yay! Woohoo!
So the way Tesla coils work is they use something called a transformer. Let's say we have two coils stacked on top of each other like this. In the top coil, we turn on some current, which creates a magnetic field, right? In the second coil, as the magnetic field turns on, the magnetic flux is changing, which means that we get voltage in the second coil. Now the magnetic field in both coils is the same, which means that the flux through each single loop should also be the same, and the change in flux over change in time should also be the same. Now the flux for the entire coil is equal to the flux for a single loop times the number of loops. So the voltage on the first one is equal to the number of loops in the first one times the change in flux over change in time, and the voltage in the second one looks the same. We can solve for the change in flux over change in time in both cases, and we know that they're equal to each other. So we can set them equal to each other, and solving this gives us that the voltage in the second coil is the same as the voltage in the first coil times the ratio of the number of turns. So if we have more turns in our output coil, then we have more voltage. A Tesla coil works by essentially combining two transformers together, giving us a very large voltage. Power is still conserved though, so while we have a really big voltage, our current is pretty low.
Now so far we've been talking about induced magnetism, which comes from running a current. But there's also permanent magnetism and other types of magnetism, which create magnetic fields without running current.
The things we generally refer to as magnets are called ferromagnetic. In general, they'll have different chunks that have magnetic fields pointing in certain directions, called domains. If you add an external magnetic field, then you can get these domains to align, giving you a permanent magnet. Examples of this material are iron and cobalt. The next type of magnetism is paramagnetism. The magnetic fields are usually randomly aligned on a paramagnetic material, canceling each other out. But if you add an external magnetic field, then the material will align with that, giving you a slight extra magnetic field, but it goes away once you remove the field. Examples of paramagnetic materials include aluminum and oxygen. Lastly, there's diamagnetism, which is present in almost all materials. To understand this, you can think of the electrons moving around an atom in these materials as tiny current loops which create tiny magnetic fields. In diamagnetic atoms, the electrons are paired up so that the magnetic field cancels out normally. But when you bring a magnet close to them, you get induction from Faraday's law. So the current running in the direction opposing the magnetic field, that electron that's spinning against it gets slightly stronger, and so the material creates a magnetic field slightly opposing the magnetic field. Examples of diamagnetic materials include water and most organic materials. And if you can get a strong enough magnetic field, you can make things levitate. For example, we've been able to make a frog levitate with a strong magnet. Just like one of these coils of a transformer creates flux through the other coil, it also creates flux through itself. Specifically, the flux is proportional to the current that we send through the coil, and the voltage is proportional to the change in current over change in time. This is actually the secret third circuit component that we didn't talk about earlier, the inductor. Since it opposes changes in voltage, one way to think of it is to imagine one of those super big and heavy wheels on like a bank vault or something. So when I start pushing it clockwise, it takes a minute to get going. But once I get it going, it'll keep going, even if I start pushing it the other way. Looking at the sine waves, it's going to lag behind the other voltages in the circuit, since it opposes changes in voltage. So we can shift it to the right because, remember, further to the right means further into the future. Now if we start looking at this peak right here, we can see that the voltage is at its maximum. At this point, enough voltage has been applied to get the current running through the inductor, and it'll keep running more and more as we push it more until we start pushing it in the other direction. And then the voltage in the inductor will start to slow down more and more again until we're at the peak voltage on the other side. At this point, current starts flowing in the opposite direction, and it continues to do so until we push it the other way. The equivalent to resistance for an AC inductor is its reactance, which is equal to the frequency times the inductance. In other words, a better inductor is going to oppose the voltage better. And also, if the voltage is oscillating more frequently, then it's going to oppose more and more because there's not going to be a steady state of the voltage. If we look at the circular diagram, the vector for the inductor is 90 degrees behind the voltage source. If we have a resistor, a capacitor, and an inductor in series, we can add them up and get the total impedance like this. It's the same thing as before, except now we have to subtract the reactance from the inductor, since it points in the opposite direction of the capacitor. Now, since the capacitor is capable of resisting the voltage of an AC circuit, we would expect it to have some kind of energy, and indeed it does. We can get it from a Kirchhoff loop, just like we did before. The voltage from the source minus the resistor voltage minus the inductor voltage must equal 0. Now, since all of these quantities are voltage, if you multiply the whole thing by current, then each quantity becomes power, because power equals current times voltage. Now we can get the energy by adding up the power from the inductor, or the change in energy over change in time, along some interval of time. Doing this gives us 1/2 Li squared. One last thing about the inductor is that when you first turn it on, it's going to oppose the voltage source, right? If we're talking about a DC circuit. But after some time, it's not going to oppose anything because the voltage isn't changing. So we can think of the inductor as starting out like an open switch, basically opposing all of the current running through it. Then over time, it's going to act more and more like a wire, letting all the current run through that it wants to. So far, we've seen 4 equations that pretty much tell us everything about electric and magnetic fields. Gauss's law relates the charge inside a closed surface to the flux through it. Gauss's law for magnetism tells us that we can't have a magnetic monopole. Ampere's law tells us how running currents create curling magnetic fields, and Faraday's law tells us how a changing magnetic field creates voltage. Combining this with the force equation for charges gives us the basis of the theory of electromagnetism. But there's one small problem with how we've been writing Ampere's law so far. When we create a loop around our wire, we find the current through the loop is the charges flowing through any surface bounded by that loop. If I have a capacitor charging up with current, and I put a loop right here, then the current through this surface is the current on the wire. But the current through this surface is 0, which means we get 2 different currents depending on which surface we choose. In order to fix this, we have to add something called the displacement current, which is epsilon naught times the change in electric flux over change in time. This fixes our capacitor problem because while the current is running, the capacitor is charging up, and so there's a changing electric flux through this surface, and there's also current through the original surface. And that revision gives us the final set of equations called Maxwell's equations. there's another consequence of this addition to Ampere's law. So let's say we have a vertical wire running some alternating current. Because of Ampere's law, the current creates a curling magnetic field. But because of Faraday's law, the curling magnetic field creates an electric field. And now, because of our addition to Ampere's law, the changing electric field creates a magnetic field, which creates an electric field and a magnetic field and so on, and it continues propagating in this direction. So as a recap, a charge by itself creates an electric field, a moving charge creates a magnetic field, and an accelerating charge creates an electromagnetic wave. Now you can work backwards from Maxwell's equations if you want, and eventually you'll end up getting some form of the wave equation as we would expect. Essentially, if we assume that the points on this wave only move up and down, then they should be accelerated in the direction of the curvature. So if it's curving down, then the wave gets accelerated downward at that point. The proportionality between the curvature and the acceleration is the speed of the wave squared. So if you want to, you can plug in the constants we've been working with so far, and you get that the speed of these waves in a vacuum is 3 times 10 to the 8th meters per second, which is exactly equal to the speed of light in a vacuum. These connected electric and magnetic waves are actually the same thing as light waves. One useful solution to the wave equation looks like this. It's just like the general sine wave in AC circuits that we saw before, except now we have this k times x term. This is because the wave changes with both space and time. K is what's called the wave number, 2 pi divided by the wavelength. So when you multiply that by some length, the wave traveled, usually x, and you get the angular length it traveled, which is the kind of input you would use into the sine function. Some other useful things about this wave are the linear frequency, f, which tells you how many full cycles it goes through in a second, which you can convert to from angular frequency by multiplying by 2 pi, and also the speed of the wave, which can be written as the wavelength times the number of wavelengths that occur per second, or the wavelength times the frequency. We've already seen that electric and magnetic fields store energy. That's why standing in the sun heats you up. But another thing we can look at is the intensity of the wave, which is the power per area. So basically, the intensity is asking how much energy per second can we get on some square unit of area. And for a light wave, it's equal to the magnitude of this vector, called the Poynting vector, which after some rewriting looks like this. Let's look at an example. So let's say I have a transmitter at a radio station with a power P, some frequency f, that's a distance d away, and I have an antenna with a length L. What's the maximum voltage I can get across my antenna? We can start by writing the intensity as the power over area. If we assume that it radiates in all directions, then the area is the area of a sphere, 4 pi d squared. Since d is the radius of the sphere, it's how far away we are from the transmitter. Now we can also get the intensity in terms of the electric field. So setting these two equal to each other allows us to solve for the maximum electric field. And now that we know what the maximum electric field is, we can get voltage from the electric field. We only care about the magnitude in this case, and since we want the maximum possible voltage, we'll go ahead and assume that E and dl point in the same direction. So we just get E naught times L, or this. Another type of antenna that you see a lot is a circular one like this. We'll call its radius R. So for this one, we're going to get a voltage from the induction from the magnetic field, like the moving magnet that we saw earlier. We've seen before that these two constants, epsilon naught and mu naught, are directly related to the speed of light, and they're built into Maxwell's equations in such a way that the induced electric and magnetic fields directly depend on them. Specifically for plane waves, it turns out that the ratio of electric and magnetic maximum field strength is equal to the speed of light. We've seen before that we can write up one of these fields as a sine wave, and now we can change the constants out front to include the maximum electric field, since that's something we know. Now since we're looking for the maximum voltage, this integral will just simplify to the magnetic field times the area of the loop, pi r squared. Now we can hit it with the time derivative, which introduces an omega into the equation, which is the same thing as 2 pi times the linear frequency, f, which is something that was given. Now lastly, since we only want the maximum voltage, we'll just consider the amplitude of the sine wave, not the sine wave itself. Now one weird thing about light waves is that they actually carry momentum. This is the equation that we use for momentum of an energy wave. The energy per volume of the wave is equal to the momentum per volume times the speed of light. This is actually a result you get from quantum physics, but there's still some kind of intuition you can get for where it comes from. So we know that momentum is mass times velocity, and also force is mass times acceleration, which means that the force is the time derivative of momentum for constant mass. Or we can rewrite that the momentum is the accumulation of the force over time. Now the energy is the accumulation of the force across some distance. So if we're dealing with changes in momentum, we'll assume that the force is in the same direction as the motion of the object. Now, we can rewrite a small unit of length as the same as change in length over change in time times a small unit of change in time. And this differential right here is just the velocity. If the velocity is constant, which it is for a wave just floating around in free space, then we can pull it out. And now we just have the momentum integral. So the energy is equal in magnitude to momentum times velocity, which for a light wave is the speed of light. So we can plug in our energy density, which is twice the energy of one of the fields, and divide both sides by the speed of light. We'll rewrite the momentum per volume in this differential form. Now, if we have some chunk of volume, dv, it's the same as the area times the length, which is the same as speed times a small change in time. In other words, dv over dt is equal to the cross-sectional area times the speed of light. Now if we have the change in momentum per unit volume times the change in volume over change in time, then we can multiply them together to get the time derivative of momentum, or the force. Usually, we'll divide both sides by the area here, and instead write the pressure from a light wave. Usually this isn't a whole lot of pressure, but it has the benefit of being kind of free. I mean, the sun is just blasting sunlight at us all the time, and we've been able to make these solar sails that are propelled by sunlight. Now we can start tracing out the path of light waves. So when a light wave hits an interface between two materials, some of the light will usually be reflected, and it reflects in such a way that the angle to the surface normal is the same in both cases, so these two angles here are the same. Most real objects don't look very reflective because they aren't this smooth. Instead, they have a rough surface, and when you zoom in far enough, the light just bounces in all sorts of directions. Now one application of this is that if you get a reflective corner material, like this, then the reflected light is always going to come out at the same angle as it came in at, which is pretty helpful if you want to send light waves back and forth. When we went to the moon, we put some corner reflectors on it, and now we can use those along with the speed of light to determine things like how quickly the moon is drifting away from us. In addition to reflecting, some light is going to refract, or go through the surface. Since light's no longer traveling in a vacuum, these two constants might change in the material, which will change the speed of light. So we defined a quantity called the index of refraction, which is the ratio of the speed of light in a vacuum to the speed of light in this new material. So when light enters a new medium, it bends according to Snell's law. The original index of refraction times the sine of the incoming angle is equal to the second index of refraction times the sine of the outgoing angle. In a real material, some of the light is going to reflect and some of it's going to refract. We can figure out the angles with the two laws that we just saw. But there's a problem with this. The larger I make my incoming angle, the larger the outgoing angle. If I can make my incoming angle large enough, then my outgoing angle is actually going to be larger than 90 degrees, which means that instead of refracting, all of the light gets reflected. We can calculate the angle this is going to happen at with Snell's law. So let's look at an example. Water's index of refraction is about 4/3, and the air's index of refraction is roughly 1. So what angle do we need for an underwater light ray to start to have total internal reflection? We can start with Snell's law. We know the outgoing angle needs to be 90 degrees or larger, so for the smallest angle we'll just use 90 degrees. Now the sine of 90 is 1, so that term goes away. Now we can rearrange, and we get that the angle is about 48.6 degrees. But what if we went the other way? Well, we could just do the same steps, but this fraction right here would be flipped. Now remember what a sine wave looks like. It just oscillates between 1 and -1 like this. We need to find the angle because it's an output of 4/3, but 4/3 is above the sine wave. In other words, there's no angle that's going to make that happen, which means that there's no angle that's going to give us total reflection from air to water. And in general, total internal reflection only works when you're going from a material of higher index to lower index of refraction. Now in some cases, even when you're tracing out the path, you still have to worry about the wave properties of light. And one useful property is interference. When two waves meet up in the same location, they add together. So if their peaks and valleys match up, or they're in phase, then the resultant wave is larger. And this is called constructive interference. But if they don't match up, then the resultant wave is smaller. This is called destructive interference. One place this shows up in is double-slit experiments. So if you have a source area emitting light through these two slits, since they're coming in at the same source, we're going to assume that they start out in phase. Now the difference between the lengths of the two paths will tell us if they're in phase or not. Specifically, if the path difference is an integer multiple of the wavelength, then they'll add constructively because the peaks and valleys will still match. But if it's a half multiple of the wavelength, then they'll add destructively. What you'll see on a detector is certain bright spots where the waves add constructively because of the path length differences. Another useful application is X-ray diffraction. So if you have some kind of material that has a grid-like or lattice structure, and we shine some kind of light waves into the lattice, if we assume that the light waves reflect like this, then the path length difference is equal to the length of these two segments, or the distance between atoms times the sine of angle 1 plus the distance between the atoms times the sine of angle 2. If we know the wavelength of the light, and we send in the light at some specific angles, we can determine how far apart the atoms are on the lattice.
So there you go. An entire physics class in a little bit over an hour. Alright, bye.